Hello, everybody. Today we're going to talk about topic 1.13, removing discontinuities. So we're going to take a look at the original function. We're going to then try to make that original function as continuous as possible. Okay. So if we take a look, I have a series of problems here. There's three. We're going to take a look at what discontinuities they have, and then we're going to try to rewrite that function to then be continuous over all real values. So if we take a look at the first function, which is rational, all right, and I have x squared minus x minus 12. So let's first identify where these discontinuities are going to happen. So x squared minus x minus 12 all over x minus 4. If you factor the top, so x minus 4, x plus 3, all over my x minus 4, your x minus 4s cancel. All right, excuse me there. So then I'm just left with my x plus 3. Now the extended function, I don't want to call it f of x because f of x is already something else. You can make it g of x, you can make it a different name if you want, but my extended function here is going to be x plus 3. So if I graph this, I'm going to start at 3. It's linear. It has a slope of 1. Okay. Now, the original graph had a hole at 4. Okay. So the original graph had a hole there, but the extended function is now a linear piece with that hole filled in. That's ultimately what an extended function is how can I write this so that it is ultimately the same but without the original discontinuities. So what we did is we took a function and we simplified it in a way so that any discontinuities that were in it are no longer. And now every value from negative infinity to infinity, or in the domain, is going to be continuous. All right, so let's take a look at the next one. All right, so I have a linear piece. So I'm going to start at 1. So the left side, actually, the piecewise starts at -1. So if I plug in a -1, 2 times -1 plus 1 is going to be -1. And it's going to be an open circle. If I plug in a -2, I get -3. Which makes sense because it has a slope of 2, right? So we know that this linear piece is going to look a little something like this. So now the right side is going to be a quadratic. It's going to be a quadratic shifted left 1, down 1. So it's actually right where that point is. And I'm going to, if I plug in 0, I get 0. So it looks a little something like this. And now I want to make this continuous. Now there's a very easy way to do this. All I need to do is define that missing point, right? The left side and right side link up. There's a removable discontinuity there. But the question is, how do I fill in that removable discontinuity? So I am going to write this function to be a 2x plus 1, where x is less than -1. I'm going to say I have an x plus 1 squared minus 1, where x is greater than -1. And if you want, you can put in that point. Okay, now you can either do it with an inequality on one of those ends, that would make one of the point, or you can straight up just make a point on your graph. So I can say, okay, I want to be at -1 when x equals -1. That would also fill in this coordinate of -1, comma -1. Okay, so ultimately we just added a piece to our piecewise function. Again, you can do that by making one of the inequalities equal to, or you can just add in a point to your piecewise function. Again, we're trying to create an extended function. That's simple. Last but not least, okay, we have sine of x. I don't know if you remember on a notes a while back, but sine of x looks a little something like this. So this is the graphical representation where this whole if you will, is at 0, comma 1, right? So we need to fill that hole in. So I'm going to do it the same way that I did. I can say, okay, I have sine of x over x for all values that are not 0, right? That's every value except for where it crosses the y-axis. And I'm going to put a point. I'll use a different color here. I'm going to put a point at 1, when x is 0. And what it's saying is it's going to put the point in at 0, comma 1. And now if you look at my graph, that graph is now continuous, right? So we're trying to find creative ways to take a graph that's now, or a function that's not continuous at a point, and make it that way. All right. Now, here are some very important problems. These are very popular amongst the AP exams of finding missing coefficients, right? So I'm telling you that it's continuous at 1, right? I want to know it's continuous over all real numbers. So how do I find that value? Well, definition of continuity states that the limit as x approaches 1 from the left, in this case, has to equal the limit as x approaches 1 from the right, in this case, right? So if I do this, if I do the limit as x approaches 1 from the left, that's going to be a 3 times 1 squared. And if I do the limit as x approaches 1 from the right, I actually have it backwards. Sorry about that, guys. Left is actually going to be the second piece of the piecewise in this case. Not that it changes too much, but I want to be good. So I have a times 1 minus 4 is the left, and then 3 times 1 squared is the right. So I have a minus 4 is going to equal 3. Add the 4 over, I know a has to be 7. So we're finding a missing coefficient such that it's going to be continuous over all real numbers. Now, if you were to double check that, you can check those limits. They will give you the same value. All right. So we're going to do the same thing for B. All right. Now I know 2 is continuous. I know this is linear. That's continuous. I know negative 2 is continuous. But I want to find A and B such that these all link up. So I'm going to start with the first two pieces. I know the limit there we go, as x approaches negative 1 from the left of f of x has to equal the limit as x approaches negative 1 from the right of f of x. And if I do that, from the left is 2, and from the right would be a times a negative 1 plus b, which doesn't necessarily help us solve yet, but it will. So I have a negative a plus b. Now the same thing, I'm going to set up the same idea. So the limit as x approaches 3 from the left of f of x has to equal the limit as x approaches 3 from the right of f of x. And if I do that, I'm going to get a times 3 plus b, which is going to equal negative 2. Or in this case, 3a plus b equals negative 2. So now I have two equations that have a and b. So I'm going to just create a system of equations. Okay, so I have a negative a plus b equals 2. I have a 3a plus b equals negative 2. I'm going to use a little elimination method here. If I multiply everything by a or 3, right? So multiply the top equation by a 3. The bottom equation can stay the way that it is. Might have been a while since you've solved this system. I get now 4b equals 4. Divide, I get b to be 1. Now I can back substitute into one of the originals. So negative a plus my b, which is 1, is 2. Subtract the 1, divide the negative, and I get a to be a negative 1. So this is how I find two variables. Ultimately, you just get a system of equations that you have to solve. But you can see that I did it the same way. Is I set up that limit expression because I know it's got to be continuous, so I know the limit has to exist. And when you set up that two-sided limit equation, it leads you into what those coefficients will be. Okay, so Writing extended functions and finding missing coefficients so that it is continuous is kind of the name of the game for topic 1.13. All right, let me know if there's any questions. Have a good day.